Есть ли звук? Вроде должен быть. Хорошо. Okay, so there is one more section in the chapter about the tensor product. So the section, if I remember correctly, 3.4, algebras. So what's an algebra in general? So definition. Let R be a commutative ring. An algebra over R, or sometimes people say R algebra, is an associative ring let's call this ring A for associative, which is a module, or which is an R module. And also we need the additional requirement. Well, when you take two elements, say x and y, in the associative ring A, you can do the following. You can multiply by an element in the ring R, and then you just can put parentheses around the product, or you could parentheses around x and r, or you can even move this and say this is the same as the product of x and ry. So this is the condition. So we're going to see several examples in a second. But before we do the examples, we can reformulate this condition a little bit, so we can notice that, so that's the end of the definition. A is an R algebra if and only if there is a map, a ring map, of course. There is a ring map from the ring R to the center of the algebra. So you can immediately check that these two conditions are equivalent. Okay, so and the important remark for us that in particular a commutative ring S is an R algebra if and only if there is a map of the rings from R to the S. Right, so in this case, if this is a commutative thing, the center just coincides with the algebra, so it's equivalent to saying that there's just a map like this. So in commutative world, it's very easy to think about the algebras as just a ring with an additional map. So what would be examples? So let me give one commutative and one non-commutative example. So in these examples, R is fixed, as in the definition. So first example is the following. So let's start with the general non-commutative situation. So let M be an R module. Then we always have the following non-commutative in general. It's not there's no non-commutative. So algebra A, which is just the endomorphism algebra over R of the module M. You've probably seen this algebra many times before. Right? So it's just the maps from the M to the M, and the algebra multiplication, just the composition of the maps. So that's a non-commutative algebra over ring R. A special case is the following. So if you assume that M is just a free module finite ring, so then this endomorphism algebra is exactly the same thing as the matrix algebra of the size n over the ring R. Indeed, for a free module, any endomorphism, if you just choose a basis, right, you use the standard procedure how you can associate the matrix with an endomorphism, you get a matrix associated with any endomorphism, and in fact it will be isomorphism of rings. So endomorphism in this case is the same thing as the matrix algebra. And the second example, also very simple. So here you can take S to be just a polynomial ring, say on finitely many variables. You can take infinitely many variables if you want, but that's an example of algebra over R. So this is commutative R algebra. Of course, you can construct many more examples. For example, you start with such polynomial algebra and then take quotient by some ideal. This is still an R algebra. Yeah, so next thing I want to do, I want to give another definition. It won't be so important at the moment, but it will be important later. So in algebra, now let's restrict our attention to the commutative situation. Commutative R algebra is called finitely generated, or sometimes people say of finite type. Let's say that a commutative R algebra S is called finitely generated if this S is in fact isomorphic to the polynomial algebra on finitely many variables, and then I take quotient by some ideal. So finitely generated means I can exactly choose finitely many generators, but in the sense of algebras. In the sense of algebras means that I need to consider polynomial ring in the commutative case. Or maybe you can compare this definition with the second definition. So second definition is the following. A commutative R algebra S is called finite if S is a finite R module.
So there finite and finitely generated is different things.
Yeah, so the word finite used in two different ways. So in the first part of the definition, this is finite as an algebra. So meaning I can, in algebra, for algebras, I can use only finitely many generators. Here, this is finite in the sense of modules. So for example, maybe we can do several examples. So if you take the simplest possible polynomial ring in just one variable, very clearly this is finitely generated. But not finite. Right, so this module, this is not a finite module over R, because as a module, well, you can say that this is isomorphic as a module to the infinite sum of the copies of R, and say this is, well, I take, for example, as many copies as I have natural numbers. So this is definitely not a finite module. So second example, so let's take an example where we have a finite algebra. Well, probably the simplest possible example you can think of is the following. You take as a ring to be, say, rational numbers, and as an algebra, you take rational numbers and just adjoin the square root of 2. right? So S as an R module is just a two-dimensional vector space. So it's finite as a module. And you can, for example, generalize this as follows. You can take R to be, say, integers, and S, again, take integers, and then adjoin the square root of 2.
And there S is finitely generated and finite.
So this is finite,
Yeah.
and you can notice that every finite algebra is in fact finitely generated. So little exercise. Any finite algebra is finitely generated. Okay, and I want to consider one more example because I want to show you one thing that you probably haven't seen in linear algebra. So this is the following example of an algebra, which is an associative algebra, not commutative, of course, in general. So let M be an R module. So the tensor algebra of M is the following thing. So the notation is T for tensor. If you want to indicate over which ring you consider this algebra, you write this R as a subscript, and then the argument is the module M. And by definition, this is just the direct sum of all the tensor products of the M with itself. So here, of course, there is a question: what's the meaning of this symbol when k is equal to 0? Well, by definition, we assume that M to the tensor power 0 is just the ring. This is how this degree 0 part is defined. And by the way, this will be a graded algebra, but I don't think that we're going to use any graded structure here. So this is how this is defined as a module. Now we can also define multiplication So what's the general element in this tensor algebra? Well, this is something like a product of x1 tensor with x2 tensor, say xn, right? So that would be a simple tensor of degree n, and of course the general tensor will be just a finite sum of such tensors. But if I want to multiply one such tensor and another such tensor, and by the way, notation for the multiplication is the same symbol, the tensor product. So this is the product in the tensor algebra. But for simple tensors, the definition is quite straightforward. This is the so-called concatenation of tensors. So maybe this is of a different degree m. So the answer is just the tensor of degree n plus m, where you just forget all the parentheses you put around these tensors. Right? So in this way, the tensor product gives us multiplication from the... By the way, there is also standard notation. If you want, you can use notation degree k part of the tensor algebra, and this will be just the tensor power k of the module m. So this tensor product is from the degree n of m. Okay, maybe I write it like this. And of course, you can convince yourself this is an associative product. If you don't have a simple tensors but general tensors, you can just use distributivity to open the brackets. So this is a standard definition of a tensor algebra, with such concatenation product. What would be an example that we know very well? Well, this is the following. Say M is a free module. So what's then a tensor algebra of a free module? How we can describe this equivalently? Well, I can say that this is the following algebra. I use as many variables as I have elements in the basis here. Well, essentially the basis in this module is generators of the algebra, but I use different parentheses, well, this angle parenthesis, and this just means that I consider this as a polynomial ring in these variables, but the polynomial is not commutative. So this is non-commuting polynomials. And that's probably what you already know from your linear algebra class. Well, in this example, there is no difference between any ring and a field, right? Over a field, you get the same answer. But over a ring, you can have modules which are not free. So, and for this, we have the following kind of easy proposition that allow us to describe tensor algebras for not necessarily free modules. Before I actually do the proposition, let me also notice that the construction of the tensor algebra is functorial, meaning that you can also can apply this construction to maps between modules. So if you have a map F from module M to the module N, I claim that there is a map of the corresponding tensor algebras which is very easy to define. You just take a simple tensor and apply F to each factor, and then extend by linearity to all tensors. So T of F, if you want to apply this on some simple tensor, maybe I use notation M. So this is M, and this is M. So this is exactly the same as we define tensor product of two maps. But in this case, the maps are the same, and I just take n copies of the same map F. If you try to define the tensor product of n copies of the same map F, you get exactly this answer. And then extend by linearity.
So can I ask a question about the use of algebra? Do you assume that algebras are unital or?
Yeah, so of course there is element 1, which is, well, you consider n equal.
Do you consider our algebras unital?
Yes, all algebras that we consider are unital. So it means that there is element 1 in all algebras. So, and if you want to understand element 1 in this algebra, well, you can just take degree 0 part, which is the same thing as the ring. And in the ring, you have element 1. So you can consider this element 1 as an element. So element 1 here is the identity. Okay, so with this construction, we can formulate the following proposition. So proposition. Let K, M, and N be a short exact sequence. So then the map of algebras, so let maybe call this first map between M and N to be F again, as in the definition. So then we have the map T of F from the tensor algebra of M to the tensor algebra of M. So then the map is surjective. Of course, this is as a map of algebras. So surjective map of algebras. Well, I haven't said what's the map of algebras is, but I think the definition is quite clear. It's just a map of associative rings, which is also a map of R modules. So this is a surjective map of algebras, and also the kernel of this map is the two-sided ideal generated by K.
What's with two-sided?
Well, in general, if you have a not necessarily commutative ring, the left and right is different, so you have three definitions for ideals. Right, so you can take an abelian subgroup inside an associative ring, and then you have the following conditions. You can ask that when you multiply on the left, this is inside the ideal. When you multiply on the right, or when you multiply on both sides. So we have three definitions. Well, the first definition, for example, means that this abelian subgroup will be a left submodule when you consider A as a left module. This will be a right submodule when you consider A as a right submodule. And this will be a bimodule if you consider A as a bimodule over A and A again. And also, if you consider a map between two algebras, A1 and A2, some map, and then of course you can take the kernel of this map, then the kernel is a two-sided ideal. So this is why they are important, and in this case, of course, we consider the kernel of some map, so it has to be a two-sided ideal just from general considerations. The point is that we can describe this two-sided ideal as an ideal generated by K. So if I want to generate an ideal by some, say, subset, I just consider, for example, the smallest possible two-sided ideal containing K inside. Or I can consider all possible two-sided ideals containing K and take the intersection of all such ideals. But the kernels are always two-sided. Okay. Well, for the proof, I just want to say that this is clear. But maybe let's spend a minute to understand why this is clear. Well, first of all, the fact that this map is surjective, I think it's indeed clear, right? Just if you look at the definition of how we define T of F, right? Whenever we have a simple tensor in the image, well, because F is a surjective map, any such element will be F of something, right? So we just see that for any simple tensor, this formula like this will be true, right? For some M1, M2 up to Mn. So this map is clear. And for not necessarily simple tensors, you can just do for every summand the same thing. So the fact that this is surjective is clear, but what if you look at the kernel? Well, maybe for the kernel I need to write something. So let's take kernel of this map. And now for the kernel, let's consider a degree n part. So meaning that this is exactly all elements in the kernel, which is also lie in the degree n in the tensor algebra. So what's this thing? Well, if I, for example, take a simple tensor here. How I can characterize that this thing is in the kernel?
Image of some x, y, I is 0.
Well, just let's think about this K as a submodule inside M. So this is kind of the embedding of the submodule inside module. So here these elements are in the module M, right? So all this x1, xn are in the module M. But what conditions I need to put on these elements to say that this is in the kernel?
Well, because sum of xi is placed in the k.
Well, 1 would be enough, definitely.
Yeah, one.
Such that, well, there is some index I, such that xi is in the k. But if you try to characterize a two-sided ideal, you take a two-sided ideal generated by k, right? And then you take again the component of degree n. What will you get? You get exactly the same description, right?
What about non-simple tensors?
No, for non-simple tensors, you kind of do the same computation.
They're not generally can be represented as simple tensors, so it's not clear why they would lie there, or why they have this heuristic.
Well, let's leave this as a little exercise. I don't really want to go into this stuff about non-commutative algebras, but actually this works in the same way for non-simple tensors. You don't really need to change the argument if you think about this. Okay, so the only reason why I wanted to even mention this proposition is the following. What would be the application? Well, what if I take, so example, what if I take a finitely presented module? So I have some Rm, I have some Rn, I have a matrix A, and the co-kernel of this matrix is a module M. So what would be the tensor algebra for such module M? Can we describe this algebra using generators and relations?
It's tensor of Rn.
Yeah, so this is first of all the free tensor algebra. So let me write this. I want generators and relations. So I write this as a algebra on non-commutative polynomials.
Quotient by Rn.
Well,
Quotient by
let's say that I take an ideal generated by m elements. This is a two-sided ideal and generated by this set of m elements. So, and what would be the formula for this, say, fj? Well, this is exactly the linear form given by this matrix on the basis x1 up to xn. So if I use the xi, I, j, so these are the relations. So tensor algebra of a module in general, this is a quotient of a free algebra of non-commutative polynomials on n variables, and then we have a quotient by the ideal of these linear forms. So of course over a field is not very interesting, well, because over a field there are no such modules. Well, in this case M still will be a free module of the rank n minus something, depending on the rank of this matrix. So over field we cannot see this characterization of the tensor algebras as quotients. So tensor algebras of quotients are in general the quotients of linear algebras modulo linear relations. But of course in general you can take this algebra and take a quotient, say, by quadratic relations, by cubic relations, etc. So it's not necessarily that we always have these linear relations. But if you have a quotient of a tensor of this free algebra by linear relations, and in fact means that secretly you're just working not with the tensor algebra of a free module, but the tensor algebra of such module with representation, where you can read this matrix presenting this module from the coefficients of these linear relations. Okay, maybe we'll do another example. So this is example 1 and example 2. This is just an example of this example. What we can say about the tensor algebra of a cyclic module. Well, there are two ways to compute this, but if you just use this proposition or previous example that follows from the proposition, we can say that this is the tensor algebra on one generator, which in this case, is if you have only one generator, then commuting or non-commuting polynomials are the same thing. So there are no difference for one variable. So this will be just polynomial ring in one variable, and then I need to take a quotient by the Ix.
If we have injection map, is it induced injection map in algebras, tensor algebras?
Not necessarily.
Oh, okay.
So this is the answer that we get if you just apply the proposition, but we can also see that this is the same as R, right? So because this this is I times X, so there is nothing in the degree 0, and then if I consider degree 1, 2, and all other higher degrees, and then everywhere I'll get quotients of R modulo I. And of course, this will be, you get the same answer if you just try to compute the tensor power of a cyclic module. If you haven't seen this before, do this as an exercise for n equal to 2. And then for all other n, it will follow by induction. Okay, so last definition. So if A1 and A2 are algebras, then we can define tensor product of algebras in the tensor product of algebras, the tensor product of algebras is the tensor product of modules with product defined by the following formula. So suppose you have two simple tensors, and you want to multiply these two simple tensors. Well, by definition, you say that this is the product of A1 and B1 and A2 and B2. So this is how you define product on simple tensors, and then again you extend by linear, well, in this case by distributivity, to all tensors. And again, you can check that this is an associative product, and it has the identity element, which will be just the product of 1 and 1. So, and indeed, this will be a new R algebra. Examples are the following. Well, for example, if S is a commutative R algebra, you can take the tensor product of S over R, say with the matrix algebra, over R, what will be the answer for this tensor product? Yeah. So as an algebra, this is isomorphic to the n by n matrices over S. Well, for modules, this is of course clear. This is just a free module of the rank n squared. You take a tensor product with S, you get again a free module of the over S of the same rank. And for algebras, well, for example, you can choose standard generators, the elementary matrices, and check that if you take the tensor product, everything is preserved from the point of view of multiplication. So this is the first example. And the second example is the following. You take a polynomial ring in n variables. You take polynomial ring over the same ring R in other m variables. Take a tensor product over R. What's the answer?
Polynomial ring of x1.
Yeah, polynomial ring over all these variables.
And why is xi commutes with yj?
By definition.
Yeah, so indeed, if this tensor product is a nice operation when you consider commutative rings. So for example, you have this. So, but immediately from this example, you can see what if n is equal to 1 and m is equal to 1, this will be just tensor algebras, right, on one variable and again on one variable. Tensor product will be a commutative polynomial algebra on two variables. But this is far from the tensor algebra on two generators. So if you try to write something like this, or maybe like this. This is of course completely wrong. This will be just a kind of part of a full tensor algebra such that tensors from here are commuting from the tensors from here. So this is...
If you take two rings on polynomials on one variable and then multiply the tensor, you would get a tensor algebra of two generators.
No, I'm saying that if you take one variable here, you can think about this as polynomial rings, or you can think about this as tensor algebras on one generator, right? So that would be a special case of this not correct isomorphism, right? So if you do the tensor product, you get polynomial algebra in two variables, which is of course not the same thing as a tensor algebra with two generators. So what I'm saying is if you try to write something like this will be completely wrong. So it means that tensor product is something that works nicely for commutative rings, but for associative rings, well, you kind of need to replace this operation. There is the so-called free product of associative rings, and if you take a free product, then you can put isomorphism here. But that's a different operation. Okay. So finally we finished this chapter about tensor products. And today we're going to start a new chapter, which is also quite general. By the way, I haven't mentioned this, or maybe I mentioned it and I don't remember, that the construction of tensor product of course makes sense in a non-commutative situation. It's a little bit more subtle. If you want to define tensor product of two modules, you need to take one module to be left module and the other module to be right module. And the answer for the tensor product in general is not a module, but just an abelian group. But this tensor product still exists in over non-commutative rings. So, and also these chain conditions you can define over any ring, not necessarily commutative ring. So chain conditions. So first section, chain conditions on modules. So there are chain conditions for modules and for rings. So first we're going to concentrate on the case of modules. Chain conditions for modules. So what are chain conditions? Definition. Well, probably you already know this, at least for rings. So first, a module M is called Artinian if
What spells are Artinian?
Artinian. This is after Emil Artin. So a module called Artinian if any descending chain of submodules so meaning the following: you start with a module and inside module you choose a submodule, say M0, then inside M0 you choose another submodule M1, etc. You just continue to choose small and smaller modules, and this is why it is called descending. So any descending chain of submodules stabilizes, meaning that there is a number n such that starting with this number n, all the modules are the same. So this is definition of an Artinian module, and there is a dual definition of a Natherian module. So part 2, a module is called Natherian after M in Noether. So this is just a dual condition. If any ascending chain of submodules. So in this case, it means that you have a module, say M0, then you can find the module M1 containing this M0, then a module M2 containing M1, etc. Any ascending chain of submodules again stabilizes. In the same sense, that there is a number such that starting with this number, all the modules are the same. Okay, well, maybe I add the third part for the in this definition the following: a ring is called Artinian or Natherian if it is Artinian as a module, or Natherian respectively. Yeah, the module itself, yes. So it means that you can apply these conditions for ideals. So for ascending or descending chain of ideals. We can say, of course, that over a not necessarily commutative ring, you have two different versions. You have version for left and also a version for right modules. Okay, let's do examples. Let's fix a very simple ring. So in these examples, the ring R is just the ring of integer, neither. How about this chain? So if you consider this chain, is it ascending or descending? So if there is an infinite descending chain, this is not Artinian. So Artinian, sorry, not Artinian, not Artinian, but how about the second property? Is this Natherian thing? Yeah. So this is not Artinian, but Natherian. Okay. So second example, Z modulo NZ. Good. So this is Artinian and Natherian. So third example is a little bit more interesting. So here we consider the Bruffer group. I'm not completely sure that I pronounced this correctly. So the Bruffer group, well, why I'm calling this group? Well, because this is Z modules. This is the same thing as abelian groups. So this is called group. So this is the following object. First of all, you consider this. So you take integers and you adjoin 1 over p. P is a some prime number to the integers. So in the sense, this is just a polynomial in this symbol 1 over p. But of course, if you want, you can write this as a set in the following way. This is m over p to the n. So this is just some rational number. M is integer. So let me just write this. M is integer. And n is some number, positive integer. Well, not negative integer. So I also need to say that P is prime. But this is not the Bruffer group. This is just very simple, this is a simple object. The Bruffer group is the quotient of this thing. So this is, let me say maybe the Bruffer group Z, and then I add P infinity. So the definition of this object is the following. Bruffer group is just the quotient of this thing that we just defined, modulo Z. Okay, what do you think about this? Is this Artinian, Natherian, both, neither?
Neither.
No? Well, this example is interesting, so let me just give you an answer maybe in the beginning. This is Artinian, but not Natherian. So, is Artinian but not Natherian. Well, and to show this, we're going actually to do even more. We're going to find all the subgroups here. There's a list of subgroups. So the complete list of all subgroups or submodules. Abelian groups and Z modules are the same thing. Okay, so this is the same. So this is the list that has the following well, maybe the short notation for this would be the following. I can write 1 over Pn z, and then I need to take the quotient by z. But for this 1 over Pnz, of course, you can give the same description as before. You can just say this is all the rational numbers of the form m over Pn, such that in this case n is fixed and m is an integer. Well, clearly, if you just look at this list of subgroups, you'll see that, of course, m0 is just the same as 0, and then you have increasing list of subgroups. And
why there's no other subgroups?
that we're going to show in a minute. But let's see that if this is correct, if this is the complete list of subgroups, then we see that this is Artinian, but not Natherian. Right? Why this is not Natherian? Oh, this is an infinite increasing as well, the ascending chain of subgroups. Right? So this can be Natherian. And why this is Artinian? Well, because if you choose some submodule, right, and try to construct a descending chain, well, you start with some mk, and this will be only a finite chain of submodules, starting well, maybe with m0 and then up to mk. So this second part, that this is complete list of all subgroups, immediately implies the first part. So we only need to show that this is indeed the complete list of subgroups. Okay, so let's take maybe some subgroup. Right? So then we can take, well, of course, we assume that this is not 0. So there is an element here of the form m over p to the n, right? So that's a non-zero element. So without loss of generality, I can assume that m and p to the n are relatively prime, right? Otherwise I do the cancellation and get this. So this is not really a strong assumption. You can always do this. If this is true, then we know that there are, say, a and b, two integers, such that am plus b to the n is equal to 1. Okay, so H is a Z submodule. So it means that I can consider, for example, A and the class. Well, actually, this notation, if you think about this, doesn't make much sense because here you have classes modulo Z. So to have a proper notation, I need to write something like this. So if I consider this class and I want to multiply this on the A, well, this A that I have here. So how I can rewrite this? I can write this as AM, and then I can add plus B times P to the N, and then divide by P to the N. Then take the class. Well, why this is correct? Well, because what I've added is just what I have plus B, but B is an integer, so the class is the same. But I know that this is the same as the class 1 over P to the N plus Z. Right? This is by the previous line. So I see that whenever I take a non-zero submodule, whenever I have any non-zero element, I automatically have an element 1 over P to the N plus Z in this submodule. Now take maximal N such that 1 over P to the N plus Z is in this H. Of course, we have two cases. we have this maximal n or we don't have this maximal. Maybe better to write it as follows. If there is maximal n such that 1 over p to the n plus z is in H, so then this H is actually generated by this 1 over p to the n plus z. Right, and this is what we have here. This is the subgroup on this list. But if there is no such n, so otherwise, what we can conclude otherwise, if there is no maximal n? Yeah, so otherwise H is just the proof group. Okay, so this finishes this example 3. And now the last example, example 4. So maybe let's go back to this z adjoint 1 over p. What we can say about it is Natherian, Artinian. Yeah. Neither Artinian nor Natherian. Okay, and why this is not Artinian?
Well, the same example as in Z.
Yeah, so for example, so at least here inside this submodule we have a copy of Z. So this can be Artinian by the same list of submodules. And why this is not Natherian?
So you can just consider a chain that goes two directions, like all the powers of pi.
Yeah, you can do the same thing, but without taking a quotient. So, and another way to explain this would be the following. Suppose that this is Natherian. Then in the previous example we have a quotient. And we know that the quotient is not Natherian. But we're going to show, maybe today, maybe next time, that the quotient of Natherian module is always Natherian. So if you postpone until we prove this little theorem, it follows from this little theorem. But what we see in this list of examples, we constructed all possible cases, right? So we have cases of the modules which are just Natherian but not Artinian. We have a case of the modules that are Artinian but not Natherian. We have cases where there's both Artinian and Natherian. And we have a case where neither Artinian nor Natherian. So all possibilities, everything is possible for modules. And this is interesting because for rings, this is not possible. For a commutative ring to be an Artinian is a very strong condition. Artinian is in fact Natherian plus dimension 0. So for example, every Artinian ring is automatically Natherian plus something showing that this is actually a very small class of Natherian rings. Of course, in the other direction, there are plenty of examples of not Natherian rings, Natherian rings which are not Artinian, for example, some polynomial rings in one variable, two variables, etc. But for modules, there are no such theorems. For modules, these are independent conditions. Okay. Now, let's prove a theorem. Characterization. 3 ways to characterize Natherian modules. So theorem let M be an R module, then the following are equivalent, the following 3 conditions. So condition 1, any submodule of M is finite. Notice that in particular, module M itself is finite. So condition 2, M is Natherian, meaning that I use the definition without with a chain of submodules. So M is Natherian. And condition 3, which is closely related to condition 2, is saying the following: any non-empty subset of modules, of submodules of M contains a maximal element. A maximal element. So proof. Let's prove that 1 implies 2. So we need to show stabilization of any chain of submodules. So let M0, M1, be ascending chain. Well, in this case, I claim that we can take the union of all these submodules, and since this one sits into another, this is again a submodule. So this union is a submodule, and we know that any submodule, well, we assume condition 1, so we know that any submodule is finite. So it means that I can generate this by finitely many elements. Let me call them x1, x2 up to xk. But each of these generators, well, because this is an infinite union, so x1 belongs to one of these mi's, right? x2 belongs to some of these mi's, and the same is true for all of them. So there is number n such that x1 up to xa are all in the mn. But if these elements are all in the mn, it means that when I take the union with mn plus 1, it doesn't change anything. It's still the same module. So mn, or maybe let me write it like this. So the submodule that is generated by these elements is equal to the mn is equal to the mn plus 1, etc. They all coincide and have the same set of generators.
What sense there is maximal element there is a set of any submodule?
Maximal by the inclusion of submodules.
Oh, okay, so.
Okay, so now we need to show that 2 implies 3. Well, I think this is relatively easy. So let S be a non-empty subset. So let S non-empty be a set of submodules. So this is a set of submodules without maximal elements. Well, we just then do the following. You choose, say, M1 in the S, right? Because there are no maximal elements, so this M1 is not maximal. So M1 is contained in the M2, right? Then you do the same thing for M2, for M3, etc. And you get an increasing sequence. Oh, and you get the ascending, not the increasing sequence, but ascending chain. So continue do this, and this will be the ascending chain of submodules. In fact, if you just think about this, the conditions 2 and 3 are equivalent not because we work with submodules, but this is just a property of ordered sets, more or less. So the last part, 3, implies 1. Okay, now we need to show that any submodule is finitely generated. So let's fix some notation. So n is a submodule that we consider, or maybe it's coincide with the m. Now let S be the set of all finite submodules of the n. And let n prime be a maximal element. So then I can take any element, so for any x in the n, which is not in the submodule n prime, I can construct a new submodule n prime plus Rx. Right? But I claim that if I consider this submodule, it has to coincide with the n prime. Now this is because if I add submodule Rx, this is still a finite module. So this is finite, and I know that n prime is a maximal element, so it has to coincide with the n prime. But this means exactly that for any such x that I take in the n but not in the n prime, in fact I'll get that the x is in the n prime. But if any x is in the n prime for any x in the n, I can conclude that n prime actually coincides with the n. And this is the end of the proof. Okay, so next theorem is the dual version of this theorem. So let me remove condition 1. So condition 2 is now M is Artinian. And then a non-empty subset of non-empty set of submodules contains not a maximal element but the minimal element. So this is the dual version of the theorem, but we don't have condition 1 here yet. What should be an analog of condition 1 in this version? What's the dual version of the condition every submodule is finite? Co-finite. You need also to analyze this condition. So let me just put this condition here. So any quotient module is co-finite. By the way, the proof will be exercise. What I'm going to do, I'm only going to define this condition, what it means to be a co-finite as a module. But before we do this, I need to give you another exercise, which is not hard, but this is the motivation for the next definition. So exercise. So a module is finite if and only if for any family of submodules, so let's say the family parameterized by set S, so for any family of submodules such that if you take the sum of these submodules, you get the module. So if and only if for any family of such submodules with this condition, there is finite set S0 inside S, such that actually you can take this finite sum. So S is not in the S, but is in S0. So if you just look at the definition of finite module, it's not very hard to show this an equivalent condition. But now we can dualize this and give a definition of a co-finite module. So definition, a module is called co-finite if for any family of submodules, again, I want to give a name to this family. This is parameterized by the set S. So for any family of submodules such that if you take the intersection of this family, you'll get zero module. There is a subset S0 inside S such that S0 is finite, and the intersection taken over this finite subset is still a zero submodule. So if you use this as a definition of a co-finite module, now you understand condition 1 in the theorem, and this is equivalent to 2 and 3. The proof actually is not very hard, but I don't think this is something that we're going to use in this course on the seminars or on the lectures. So I don't have points to use this statement. So this is just kind of to show you how we can formulate this equivalent condition. So something that's usually missing in the textbooks. So for example, if you take Atiyah MacDonald or Altman and Kleiman, or even I think Eisenbach and Masumura doesn't have this condition. So I just wanted to show you this condition, but this condition is actually not very important for any applications. Okay, so do we have time to do anything else? Well, maybe we still have time to prove one more theorem. Which is not very hard and very natural. And this theorem is actually very useful. It's one of the basic theorems about Artinian or Natherian rings. So let M prime, M, and M double prime be a short exact sequence. Short exact sequence of our modules. Then M, the module in the center, is Natherian or Artinian if and only if M prime and M double prime are Natherian, Artinian respectively. So the proof will be for Natherian case, for Tinin case, the proof is exactly the same. Well, one implication I think is clear, right? If you know that M is Natherian, then M prime and M double prime has to be Natherian, because otherwise, if you have, for example, this infinite ascending chain in the M prime, you just use the same in the M prime. So you use the same chain in the M, right? And if you have infinite chain here, well, again, by the correspondence theorem, this will be a chain of submodules here, also infinite. So in one direction, this is, I would say, clear. So we need to go in the other direction. Now we know that M prime and M double prime are Natherian. We want to show that M is Natherian. Well, let's take this Mn, this ascending chain. Ascending chain in the M. And we can form two ascending chains in the M prime and M double prime respectively. So we can take, for example, if I give this maps names alpha and beta in the short exact sequence, then the pre-image under the map alpha of this Mn, or in other words, this is the same thing as Mn intersect with the M prime. This is ascending chain in the M prime. And also I have the ascending chain beta of the Mn. So this is inside M prime, and this is inside M double prime. So these are ascending chains. And now the result just follows from the 5 lemma. So I have 0 alpha inverse of the Mn. This is embedded into the Mn. The quotient is beta applied to the Mn. And now I need the same thing but for n plus 1. No,
theirs is ascending chain, but theirs.
No, this is for some fixed n. So this is the chain. I choose a module Mn in this chain, and I have the short exact sequence for every module Mn by the definition of this module and this module. And then I do the same for the next module, Mn plus 1. Now, if I assume that n is sufficiently large, right, I know that there is a stabilization here. So in general, I know that these things are embedded one into another. But for sufficiently large n, here there is stabilization because n prime is Natherian, so they are equal. And the same is true for these two modules. Now 5 lemma tell us that actually they has to coincide. Right? So this is the embedding, and we know by the 5 lemma this is an isomorphism, so this embedding has to be just the identity on the modules. So Mn is the same as Mn plus 1. And this finishes the proof. Okay. Maybe this is the last thing that I'm going to prove today, and we continue next Monday.